Hey there, and welcome to This Explainer. Today, we are diving deep into the actual math and methodology behind professional solar sizing. We're moving way beyond the guesswork and looking at the real, hands-on engineering that goes into designing a reliable solar energy system. We'll be drawing our insights directly from Frederick Lungu's Solar Energy Installation course. So if you've ever wondered how the pros calculate exactly what a home needs to go totally off-grid, or just set up some backup power, well, you are absolutely in the right place. Let's get started. Let's kick things off with this fantastic piece of advice from Frederick Lungu. It sounds pretty simple, right? But it's actually a massive trap that so many beginners fall into. Real solar technicians just don't guess. They calculate everything based on very specific needs. Think about it. If you size a system incorrectly, your customer either wastes a ton of money on a hugely oversized setup, or even worse, the system completely fails to meet their daily needs, and nobody wants their lights going out on day one. It is all about precision. So here is our roadmap for today. We're going to cover the core PV technologies: power versus energy, conducting a load audit, sizing panels and batteries, inverters and surge power, and we'll wrap it all up with the complete professional solar sizing workflow. First up, Section 1, the core PV technologies and how to go about choosing the right panel. Before we can even think about sizing a system, we need to understand the actual technologies that convert sunlight into electricity. Now, what's really interesting here is that a true professional doesn't ask which panel is best. Instead, they ask which panel is most appropriate for the specific job. For instance, monocrystalline panels, which you can usually spot because they're quite dark or black, are made from a single crystal structure. They have really high efficiency, making them absolutely perfect if roof space is tight. Then you have polycrystalline panels. These are the blue ones. They used to be the go-to low-cost alternative, but honestly, they're a lot less common today. Finally, there's thin film. These are super lightweight, but they demand a much larger surface area to get the job done. A pro installer is always weighing space, budget, and environmental factors like temperature. Because believe it or not, even in a super sunny location, high heat can actually lower a panel's performance. Moving right along to Section 2, power versus energy. Getting this right is literally the foundation of all solar sizing. We cannot audit a house until we firmly grasp the difference between these two concepts. Okay, here's the golden rule you absolutely have to remember. Watts measure immediate power. It's how quickly an appliance is using electricity right at this very second. So if you have a 100-watt TV, its power rating is 100 watts while it's turned on. Simple enough, right? But watt-hours, that measures the total energy used over time. If you leave that 100-watt TV on for 5 hours, you multiply the two to get 500 watt-hours. Mixing these two up is a classic amateur mistake, but keeping them totally straight in your head is the bedrock of proper system design. And that brings us perfectly into Section 3, conducting a load audit. We're going to look at a grounded example of a Malawian household to see exactly how this works in practice. Let's say a family in the Long Way wants to set up backup power. We don't guess what they need, we tabulate it. 4 10-watt LED bulbs running for 5 hours, that gives us 200 watt-hours. An 80-watt TV on for 4 hours is 320 watt-hours. Phone charging and radio add just a little bit more. But I want you to look closely at the refrigerator on this list. This is where professional thinking really shines. A fringe compressor cycles on and off all day, so you can't just multiply its wattage by 24 hours. You have to use the manufacturer's daily estimates, which for our teaching example here is 1,200 watt-hours. Tally all of this up and our target daily energy demand comes out to roughly 1,870 watt-hours, or 1.87 kilowatt-hours. Section 4. Sizing panels and batteries. Now that we've nailed down our daily energy demand, we can finally calculate our actual solar array and battery storage requirements. Now, because we obviously can't capture 100% of the sun's energy, we need a formula. To find our required array size, we take our daily energy demand, we divide it by the peak sun hours for our specific location, and then we divide it again by a system efficiency factor. That last part is super important to account for real-world energy losses. So, using a 5-hour peak sun estimate and a pretty conservative 0.75 efficiency factor, let's plug in our 1,870 watt-hours. The math punches out a preliminary requirement of exactly 499 watts. Let's just call it a clean 500 watts of PV. In the real world, you could easily achieve this by throwing up two 250-watt modules, assuming everything is electrically compatible, of course. Okay, what about the battery? You know, the thing keeping your lights on when the sun goes down or during a blackout. We take our required daily energy, multiply it by our days of autonomy, which is just how many days we want the battery to last without any sun, and then divide that whole thing by the battery voltage multiplied by the allowable depth of discharge. For this example, let's assume 1 day of autonomy, a standard 12-volt battery, and a safe 50% depth of discharge limit, which is pretty standard for a traditional lead-acid battery. Run that calculation and you get a preliminary battery capacity of roughly 300 amp hours at 12 volts. But hey, here is a real insider secret for you. A seasoned professional will tell you that as your overall system power increases, you shouldn't just stubbornly stick to 12 volts. Larger systems very often upgrade to 24 volts or even 48-volt architectures. Doing that reduces the electrical current, which means you can use smaller cables and minimize those pesky energy losses. Section 5 brings us to inverters and surge power, and this is really all about managing heavy loads. We've got our energy needs sorted, but for sizing the inverter, we actually have to switch gears entirely. Remember that whole watts versus watt hours thing? Well, inverters care about watts. They care about what's happening right now. If our household decides to turn on the TV, the lights, the radio, and the fridge compressor all at the exact same moment, our simultaneous running power hits 285 watts. This tells us immediately that slapping a standard 300-watt inverter on this system is a terrible idea, unless you really enjoy the sound of popping fuses. We definitely need to look at an inverter rated for 500 watts or more. But hold on. There's a huge catch. Heavy loads, things like refrigerators, water pumps, or maize mills, they require a massive amount of starting current. Their initial starting power can be vastly higher than their normal day-to-day running power. This is exactly why understanding the difference between an inverter's continuous power rating and its surge or peak power rating is absolutely vital. You literally can't just add 20% to your calculation and call it a day. You have to check the specific starting characteristics of the appliance against the inverter manufacturer's surge specifications. And that brings us to our final section, Section 6, the professional solar sizing workflow and the final review. Let's synthesize all of this and see how it builds into a totally reliable workflow. This overarching 6-step workflow is what guides you safely through the entire process. You start out by understanding the client's needs and auditing their loads. Then, you use those energy totals to estimate the PV and battery requirements. After that, you identify the simultaneous running power and those tricky surge loads so you can properly spec your inverter. Step 5 is all about selecting equipment that electrically plays nice together. And step 6, well, that is the most critical step of them all. Step 6 is honestly paramount. Why? Because those preliminary calculations we just did, they're really just a starting point. A true professional design requires checking absolutely everything. Are the PV module voltages actually compatible with the charge controller? Are your cable sizes large enough to prevent dangerous voltage drops? Do you have the proper DC isolators, fuses, and AC circuit breakers securely in place? Have you accounted for a neighbor's tree shading the roof or local safety standards? Look, solar electricity is incredibly powerful, which means it can be dangerous when incorrectly installed. Properly engineering a system means rigorously verifying all these protective measures before a single panel ever goes on the roof. We've covered a ton of ground today, moving all the way from basic definitions to full system verification. But reading about it is very different from actually doing it. So grab a notebook, take a walk around your home right now, and pick out 6 real appliances. Check the nameplates on the back and put